Hello there, Mr. Sutton here, bringing you the AB Calculus 510 Extra Practice Number 2 solutions on derivatives of inverses. For this problem, we're trying to find the derivative of the inverse function for this f of x at the input 3. So to start this off, I'm going to do my general inverse derivative setup. I'm going to write f inverse prime of 3 equals 1 over f prime of f inverse of 3. And then I need f inverse of 3. Well, that's what I have to plug in to the f function in order to get an output of 3. Here's the output of 3. I had to plug in 7 over 5. So down here, I've really got f prime of 7/5. And now I have to do a little more work with f prime. So the f function is originally 5x plus 2 to the 1/2. F prime then is going to be 1/2 times 5x plus 2 to the negative 1/2 times the derivative of the inner function, so times 5. Plugging 7/5 into this now, I have basically 5 halves times 5 times 7/5 plus 2 to the negative 1/2. And doing a little simplifying here, the 5s are going to cancel, so that's really 9 inside there. So just rewriting this in radical form, I can write this as 5 over 2 times the square root of 9. Well, that's really 2 times 3, which is 6, so we have 5 over 6 for that f prime value. And so that's not the answer, though, because we really have 1 over this 5 over 6 value, which becomes 6 over 5. For this one, I'm trying to find the derivative of the inverse to this function at an input of 11, and given that f of 2 for the original function is 11. So let me start with my inverse derivative setup. F inverse prime of 11 is going to be 1 over f prime of f inverse of 11. And f inverse of 11, that's what I have to plug into the f function to get 11. That's 2 according to this function call up here. So I've got a 2 in there. And now I need to talk a little bit more about f prime. F prime in general is going to be 4x. So now plugging 2 into that, we end up with f prime of 2 equaling 8. So then I can just rewrite this whole thing as 1 over 8. On this problem, I've got this cubic function, or cube root function, and f of negative 1/2 is 2. We want to find f inverse prime of 2. Okay, so let me start with my inverse derivative setup. F inverse prime of 2 is going to be 1 over f prime of f inverse of 2. And f inverse of 2 itself, that's just what I have to plug into f to get 2. Well, that's this negative 1/2 right here. So now I need f prime of negative 1/2. Okay, well, let's talk about f prime in general. F of x just by itself without a derivative, that's just going to be 2x plus 9 to the 1/3 power. So I can use the power rule to take that derivative. That's going to be 1/3 times all this stuff to the negative 2/3. But don't forget to multiply by the derivative of 2x plus 9, the chain rule here. So that's a 2 also that gets multiplied out there. And now plugging negative 1/2 into all this, I've got 2/3 times all this stuff with negative 1/2 plugged in. 2's are going to cancel in here, so this is negative 1 plus 9, which is 8. I can rewrite this in radical form as 2 over 3 times the cube root of 8 squared. And simplifying it step by step here, cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12, so this is 2 over 12, which is really 1 over 6. So then we can write this as 1 over 6, which is really just 6. On this problem, I want f inverse prime of 8, given this f of x and the fact that f of 0 is 8. So the inverse derivative setup in general, I can write that this equals 1 over f prime of f inverse of 8. F inverse of 8 is what I have to plug into f to get 8 back. Well, I get 8 back if I plug in the x value 0, so that's what f inverse of 8 is. It's 0. And f prime of 0, well, now we need to know what f prime is. Using our power rule, that's going to be 30x to the 4th plus 4. And plugging 0 into all that, we've got that first term being zeroed out, so that's just 4. So then I can just rewrite this as 1 over 4. For this problem, I'm looking to find f inverse prime of 2, given this cube root function and this 15/8 that comes out to 2 when I plug it into the f function. So let me start by writing my derivative setup in general for inverses. I can write that this expression is equivalent to 1 over f prime of f inverse of 2. And then f inverse of 2, that's what I have to plug into f to get back to. That's this 15/8 that I see here. Now I need f prime of 15 over 8. Well, let's get f prime, and even before that, let's rewrite f as 8x minus 7 to the 1/3 power. There we go, f of x, not f prime of x. So then the derivative of that, we're going to use the chain rule. This is going to be 1/3 times 8x minus 7 to the negative 2/3 times the derivative of 8x minus 7, so times 8. And then I've got to plug in 15 over 8 in for x right here, and I'll just move this 8 to be with the 1/3, so 8/3 out in front. So we have 8/3, 8 times 15 over 8 minus 7, all raised to the negative 2/3. And this looks like a big mess, but it's going to get nicer quickly. These 8's inside cancel, so I've really got 15 minus 7, which is 8. So I've got 8 over 3 then, times the cube root of 8 squared, so all that stuff in the denominator, just rewriting this fractional exponent in radical fractional form. Cube root of 8 is 2. 2 squared is 4. 4 times 3 is 12, so we have 8 over 12, which I can reduce by 4s to give me 2/3. So f prime of 15 over 8 is 2/3. 1 over 2/3 then gives us our final answer of 3/2. For this problem, given this square root function, I'm looking to find f inverse prime of 2. So that's equivalent to 1 over f prime of f inverse of 2, just my general derivative inverse setup. F inverse of 2 is going to be 1/8, because when I plug in the output 2, I get back the input for the f function, which was 1/8. Now I have to find f prime of 1/8. So f prime, I'm taking the derivative of this square root function. This is really initially 8x plus 3 to the 1/2 power. So that derivative is going to be 1/2 times 8x plus 3 to the negative 1/2, multiplied by the inner function's derivative, which was 8. And now plugging in 1/8, I can write 8/2 times 8 times 1/8 plus 3 to the negative 1/2. Let's simplify this. These 8's inside here cancel. So this is really 1 plus 3. So this is going to be 8 over 2 times the square root of 4. Well, square root of 4 is 2, times 2 gives us 4. 8 divided by 4 is just 2. So that is our f prime of 1/8. And then I can just rewrite 1 over that stuff as just 1 over 2. On this problem, they're telling us that f is this increasing crazy polynomial function, and we have f of negative 1 equals 2. G is the inverse of f. We want to know which expression is correct for g prime of 2. So in general, g prime of x is going to be 1 over f prime of g of 2. So we've got g of 2, which is going to be what I have to plug in to the f function to get back an output of 2. So it turns out they told us what that was. If you plug in negative 1, you get back 2. Therefore, g of 2 is going to be this original input of negative 1. So we can rewrite this as 1 over f prime of negative 1. And before you go ahead and take the derivative of this and plug in negative 1 and plug it back in, take a look at your answer choices. There's already an answer choice for 1 over f prime of negative 1. Choice B. For this one, we're given a table with some values for x and f prime, and we're told that g equals f inverse, so basically g and f are inverses of each other. We want to know which expression is correct for g prime of 2. So in general, g prime of 2 is going to be 1 over f prime of g of 2. So 1 over the derivative of the original function with the inverse value plugged in. What's g of 2 exactly? Well, g of 2, that's the number I have to plug into the f function to get back the output 2. So looking in my f of x row, because that's where my outputs are, when I get back an output of 2 for the f function, I had an input of 4. So that means g of 2 is this original input of 4. So I've got f prime of 4 down there. And what is f prime of 4? Well, f prime of 4, looking that up in the table, that's going to be negative 5. So I can rewrite this as just negative 1/5, which gives me answer choice C. On this free response problem, we're given this curve right here. And for the first part, I want to show that dy over dx equals 4 over 2y plus 1 quantity squared. So to do this, because it's going to be kind of annoying to isolate y, I'm just going to use implicit differentiation. So I'm basically going to take the derivative as normal, but whenever I take the derivative of something with a y, I have to multiply by the derivative of y because we're treating y as an inner function of x. So going left to right, I've got all this stuff cubed. This is a chain rule waiting to happen. I need the derivative of something cubed, which is going to be 3 times the something squared. But now I have to multiply by the derivative of the something. Derivative of 2y is going to be 2 dy over dx. Again, taking derivative of y, you have to multiply by the derivative of that, using the chain rule basically. And then derivative of 1 is just going to be 0, so we don't worry about that. And let's see here, I've got minus 24x that I still need to differentiate. That's going to be minus 24. And then finally, derivative of this constant over on the right side is just 0. All right, let's clean this up a little bit. So I'm going to just multiply the 2 and the 3 together to get 6 on the left, along with the 2y plus 1 squared and dy over dx. And I'm going to add the 24 to move that over to the right side. Basically, I want to isolate dy over dx at this point. So I can do that by dividing by all of this stuff here. And that gives me something. It's not what I wanted, though, because they showed me something different up here. But it turns out if you reduce this by 6, you do end up with 4 over 2y plus 1 quantity squared, which is exactly what they were requesting. So now we're done. On this problem, I want the equation for the tangent line for this curve at -1, -2. To get a tangent line equation, I'm going to use point slope. So I need a point, which I've already got, and I need the slope. Let me figure out the slope by plugging this into the dy over dx that they gave me in part A. Here that is again, 4 over 2y plus 1 squared. So plugging in -1, -2 to that derivative, and it turns out I only need to know the y value here. This is going to be 4 over 2 times -2 plus 1 squared. So let's see here. This is -4 plus 1 is -3. Squaring that, we get 9, so 4/9. Putting it all together in point slope, I have y minus the y value of -2, so y plus 2, equals my slope, my m value of 4/9, times x minus the x value -1, so x plus 1. And we're just going to leave it in this form because they didn't really want us to use it for anything else. For this problem part, I'm trying to take the second derivative of this curve at -1, -2. So recall from part A, our first derivative in general was 4 over 2y plus 1 squared. And the first derivative at specifically -1, -2 was 4/9. We're going to use both of these facts on this problem. So to get the second derivative, I'm going to take the first derivative and take the derivative of that. I'm going to rewrite this dy over dx first, though, as 4 times all this stuff to the -2 power, just to make it a little easier to take the derivative. So now, using the power rule with a chain rule, we have -8, this stuff to the -3rd power, times the derivative of the stuff inside, which is going to be 2 dy over dx. We're still implicitly differentiating. Y is still an inner function of x. And I'm going to clean this up a little bit before I try plugging anything else in. So I can write this as -16 over 2y plus 1 to the 3rd power. All of that times the dy over dx. I could put that up in the numerator, but I'm just going to leave it out in front. It doesn't really matter when all is said and done. So now evaluating our second derivative at the point -1, -2, I'm going to have -16 over 2 times -2 plus 1 cubed times, remember, dy over dx has its own value now, and that is 4/9. So at this point, you've got all constants. You could leave well enough alone and move on and call it a day, because this is numerically equivalent to whatever it is they were looking for. But if you want to live on the edge and simplify, our numerator is going to be 64. And in the denominator, we're going to have, let's see here, we've got 2 times -2 is -4, plus 1 is -3. -3 cubed is -27. And that negative, by the way, is going to cancel out this negative in case you were wondering why I didn't write a negative over here. So we basically have 27 times 9. Well, these are both powers of 3, so you might want to think of this as just 3 cubed times 3 squared, which is just 3 to the 5th, which you might know is 243, but if not, now you do. And we can't simplify that any further, so even by the most strict simplifying standards, we are done with this. On this last part of the problem, they're telling us the point 1/6, 0 is on the curve, and they want y inverse prime of 0. So let me just recall my derivative, because I'm going to need it here. From part A, here it is again. And now if I'm doing one of these inverse derivatives, I've got my general inverse derivative set up. I can write that this stuff is equal to 1 over y prime of y inverse of 0. Now, y inverse of 0, that's what I have to plug into the y function to get an output of 0. So when I get the y value 0, it was from plugging in the x value 1 over 6. So y inverse of 0 is this 1 over 6 input. And now I just need to figure out what y prime of 1 over 6 is. So I can use my derivative up here for that. So I'm evaluating the point 1/6, 0 for this derivative. And in order to do that, well, let's see here. This is going to be 4 over 2 times 0 plus 1 squared. This is just 1 squared down here, so just 1. So we really just have 4 when all is said and done. That's not the answer, though, because we really have 1 over this value here. So 1 over 4 for that final answer.